Okay, so we are going to do this problem. And when you look at this, it looks like, oh, LOL. We have our Br2, which is a halide, and then we have a solvent. And normally what I see, Orgo, I see water as our solvent. So we know that when water adds on to, oxygens, it forms this OH group, which is our alcohol plus H3O plus. So the same thing's gonna happen with this methanol, where we're gonna get OCH3 minus, and then the H blah blah blah. So the important thing to know is that when we solve this, our solvent at the end is going to have this on the structure, not OH. So going into that, when I have an alkene reacting with an halide, it's going to make a bridge with my halide on it, and this bridge can either form as a wedge or a dash, because in the grand scheme of things, there are wedges and dashes on everything. So I have my Br plus my other Br floating on a solution and my solvent. So the same thing is going to happen when I have my bridge form as a wedge instead of a dash. So here's my bromine, and then my other bromine, and my CH3OH. So you don't really have to draw all of this stuff out. It just helps me know what I have in my toolbox and what I'm ready to use for when I actually solve the problem. So if I didn't have my solvent in solution, I would have a completely different mechanism, but that's not what the problem is asking. So since I have my solvent in solution, this solvent is going to come and do a backside attack here onto the most substituted side of the molecule. So in this case, it's this carbon where I have a methyl group and then these two substituents of the chair structure, and then technically this little bridge thing that's coming off of it. The same thing's going to happen to the other side where I have this. And then what happens is the backside attack will cause some shifting naturally, because when there's a backside attack, this CH3OH is going to come from the back. Since this methyl group is coming out at me, that means that the backside attack has to come from here. So it's going to shift everything around. So my OCH3 is going to be up here. My methyl group is going to get pushed to the front. And then in turn, my Br is going to get, I'm so sorry, it's not focused. My Br is going to get pushed down. So here's my Br. My methyl group stays the same. And notice that my Br minus is still floating around in solution. That's fine. The solvent is much more present in solution than my Br minus. So it's almost like how the large child is able to push over the small child in order to be first in line for a pizza party. This is this. The large child is able to get in line faster for the pizza than the small child. I am the small child. I'm not able to get to the pizza fast. So similar to the left side, our right side will, oops, I'm sorry, I didn't draw the anchor here. This backside attack will occur. We're gonna have OCH3, that's not, it's gonna be a CH3 here. And then this is my bromine right here. So technically, we need to know how many products can this reaction make. So the question that I'm looking at says it can give 4 isomeric products, and it says one is formed in a much greater amount than the other 3, and you need to draw the major product. So looking at these, which one will be my major product? Well, let's redraw these products as axial and equatorial, because that is what chair structures are built on. I know that my wedges mean that it's going to go up like this. So this is my CH3, and then my OCH3 is going to go down like this. And when I redraw this one, my OCH3 is up, so it's going to go up. My CH3 is down like this, and then my Br is down like this. and then here's my anchor. So which one is major? Well, we need to see how my anchor interacts with everything that's around it. So in this case, my anchor is up, my Br is up, and my CH3 is up. So there's a lot of interference going on here, because if you look at a cyclohexane like this, even looking at just two sections of it, if there's something over here and something over here, then they're going to have more interference than something that is completely across the ring. So as you can imagine, this is not the right answer. This one is the right answer because we have, 2 out of the 3 of our substituents pointing down. And also notice how our largest substituent is also pointing down. Our anchor always needs to be equatorial because it makes the molecule more stable, so keep that in mind. But in this case, this is the more stable molecule. So this is going to be our major product, and technically we can do other products from this reaction. So if we go back to the top at this point, and I have these molecules right here. My bromines are on the bridge, everything's fine. My solvent is going to come and do a backside attack. So in real life, anything can happen. Even though we learned these pretty little rules for chemistry about the substituents, going to the more substituted side, all that stuff. Technically, this solvent could also do a backside attack right here because this is, a secondary carbon. And if it was a carbocation, as this is a pseudo-carbocation, then this could technically have a backside attack right here in order to satisfy the carbocation. It would push this bromine to this carbon instead of pushing it down to here. And then I would have my bromine and my methyl group on the same side, and I would have my OCH3 on this side. This happens in such small amounts, it literally doesn't count. But know that this can happen. So if you see something funky and you get 4 answer choices and you have to say, okay, which one is the major product? The major product would be the one that we've already talked about, these 2. And you could be given 2 other products, and one of them might have a backside attack having occurred on this bottom carbon right here. That is a correct answer in the mechanism, but it is not the major product. So knowing that this can happen, keep it in the back of your cute little brain, but don't worry about the other 2 products because the other 2 that we've already made are in such more amounts than the other 2. So I hope that helped, and let me know if you have any questions.